Okay, good afternoon, everybody. I'm going to share my screen with you now. This one here. Here it is. Can you see the screen? A sort of diagram of an inverse system. Supriya?
Yes, sir.
Yes, sir.
Okay, very good. So now, somebody had asked me last time as to what an easy example of an inverse system is. Of course, you can give some trivial examples. And here is the first non-trivial example. Okay, so I'm looking at an inverse system of sets, where the set S1 just consists of two elements, 0 and 1. The set S2 consists of strings of length 2 of these two elements. So S2 consists of 0, 0, 0, 1, 0, and 1, 1. And what is the map from S2 to S1? It forgets the first bit. These things are called bits, right, in computer science technology. So you forget the first bit and you just keep the last bit. That gives you S1. Now S3 consists of all strings of 3 bits. So from 0, 0, 0 all the way to 1, 1, 1. There are 8 such things. And what is the map which sends the map from S3 to S2? It takes a string and chops off the first bit and keeps the last 2 bits. So that's a map to S2. And you can imagine this forming an inverse system. The map Sn plus 1 consists of strings of length n plus 1, and the map takes this Sn plus 1 to Sn by chopping off the first bit and keeping the last n bits. So that's a fairly straightforward inverse system. And what is the inverse limit of this system? You can see that it's going to be bits of arbitrary length, infinite length. Not arbitrary length, because that might mean, they are of finite length, but the length can be arbitrary. No, these are actually strings of infinite length. For some reason, I'm writing them from right to left, epsilon 1, epsilon 2, epsilon 3, and so on. And these epsilon i's are, of course, these bits, 0 or 1. And actually, an inverse limit is not just a set. Excuse me, it has to be a set together with maps to the sets in your inverse system. So what is the map from this inverse limit? The limit consists of all these strings of infinite length. What is the map to S2, for example? It simply keeps the first 2 bits, epsilon 1 and epsilon 2, and ignores all the other bits. Similarly, the map to S3 is the one which keeps the first 3 bits, epsilon 1, epsilon 2, epsilon 3, and forgets about the remaining bits. So what you can see clearly is that if I start with a bit, a string of infinite length, string like this of infinite length, take its image in S3, and then the image of that image in S2 is the same thing as going directly to S2, right? Because when I go to S3, I'll keep the first 3 bits. Then when I go to S2, I just keep the first 2. So this is a basic example of an inverse system, and inverse limit consists of these strings of infinite length. Now, to show you the difference between an inverse system and a direct system, I've made the same sets into a direct system as well. So here it is. The sets remain the same, S1, S2, S3. Now it's a direct system, so the maps go in the other direction. From S1 to S2, from S2 to S3 and so on. And what is the map from Sn to Sn plus 1? Sn consists of all strings of length n. You just add 0 at the end of that string to get an element of Sn plus 1. So that's what is happening here. S1 to S2 is the map which takes 0 to 0, 0 and 1 to 1, 0. It takes 0, 0 to 0, 0, 0, 1, 0 to 1, 0, 0, 1, 1 to 1, 1, 0, etc. You just append a 0 at the end. Now that's a direct system by definition. What is the direct limit going to be? So the direct limit, as you can imagine, is also going to be bit strings of infinite length, but with only finitely many ones in that string, right? Why are there only finitely many ones? Because each element in the limit, it's the co-limit actually, in this case it's called the co-limit, is coming from some finite stage. And at each finite stage, you just have finitely many zeros and ones. But the map into the co-limit, you get it by appending zeros at the end, right? So the co-limit of this diagram is the set of all strings of infinite length with only finitely many ones occurring in the string. Of course, this diagram is not the same as this diagram. This was the arrows are in the other direction. Here, the limit consists of all strings of infinite length with arbitrarily many, any number of occurrences of 0 and any number of occurrences of 1. There is no restriction as there is here in the case of the direct system. Okay, so now I'm going to quit this screen and go to this other screen. Are there any questions about this example? Any questions about the example?
Yes, the last example is, the inverse limit is direct product of z mod to z and infinitely times, and the second one is direct sum of z mod to z. Right?
Well, that's a nice remark, yes. In a sense, yes. The inverse limit is really the same as the direct product in this case. And the direct limit is sort of the direct sum of these things. Yeah. So in general, you are thinking of these groups, but in general, products are also a kind of limit. And direct sums, these disjoint unions are also a kind of co-limit. But let's not get into that. So your remark is very perceptive, yes. Okay, now for the rest of this course, we are going to fix a prime number p. Okay, and so for every n, we have this ring z modulo p to the n z. It will occur so many times that I just give it a name. I call it an. Of course, p is not reflected in this notation, but I'm keeping p fixed. A1 is, of course, a field, and it's also denoted fp, right? Z mod pz is denoted fp when you think of it as a field. Oh, yeah. Now, there's a morphism of rings from an plus 1 to an, right? That's because of the inclusion of ideals. The ideal generated by Pn plus 1 is contained in the ideal generated by P to the n. Okay, and that inclusion of ideals gives you this morphism of rings. And this is clearly surjective. And what is the kernel? The kernel is generated by the element p to the n in this ring a n plus 1, right? So if I denote by phi n this morphism, I get this system, which is an inverse system, right? I have an maps from an plus 1 to an, and these are all homomorphisms of rings. So this is an inverse system of rings. And we'll soon define Zp as the inverse limit of this inverse system. But before we do that, we need to, I'll make one remark, which will be needed later. So let's look at this ring an plus r. So it has an element p to the r. It's actually, no, I'm looking at the element p to the n, in fact, not p to the r. P to the r is also there, but I'm looking at p to the n. It has order p to the r, because p to the r times p to the n is, of course, p to the n plus r, which is 0 in this ring, right? So this element in the additive group of an plus r has order p to the r. Now, whenever I have a group with an element of order p to the r, there's a unique morphism from Z mod p to the r to that group, taking 1 to that element, of course, right? So that's what I've written here. So there's a unique morphism of groups from AR to AN plus R, taking 1 to P to the N, because this P to the N has order P to the R. And what is the image of this morphism? It's, of course, the ideal generated by P to the N. Normally, it would be the subgroup generated by P to the N, but in these rings, the subgroup generated by an element is also an ideal. So what you get is an exact sequence. 0 goes to AR. That was the map, AR to AN plus R, goes to AN. So that's an exact sequence of additive groups. Okay. In particular, when n is equal to 1, we have this exact sequence. So if in terms of what these rings are, this is Z mod PZ, this is Z mod P to the R plus 1Z, and this is Z mod P to the R Z. Okay, but this inclusion, you have to be careful. I mean, it's not, 1 doesn't go to 1 here, right? That's what I wanted to say by when I said you have to be careful. It's not 1 going to 1. I mean, that there's no such map. 1 going to 1 is not a homomorphism of groups, because the 1 here has order P to the R, and the 1 here has order P to the R plus 1. Okay. So 1 goes to P is the map here. 1 goes to P. Okay. Any questions? Okay. So what is a p-adic integer? It's the inverse limit of that inverse system. So it is a family of elements where xn is in the ring an, and phi of xn plus 1 is xn. Phi, remember, was this map here, or phi n, I should have said, yeah, phi n. Phi n is the map here, which I've defined, right? It's the map of reduction modulo p to the n. P to the n generates an ideal here. You go modulo p to the n, and this is really the quotient of this modulo p to the n. So that was the inverse system. And therefore, an element of the limit is a family of elements, one from each of the terms in the inverse system, but these terms, these elements from the various terms have to be compatible in this sense that phi n of xn plus 1 has to be xn. Can you still hear me? We have had some problem with the lights.
Yes,
Yeah, okay, good. So the set of all p-adic numbers is in p-adic integers. P-adic numbers we will come to later. That set is denoted by Zp, and therefore by definition is a subset of this product of all these rings consisting of those xn's in this product which are compatible in this sense. Now this formula here, or this displayed requirement here, is exactly the same as this requirement that phi n of xn plus 1 should be equal to xn. This is just a different notation for the same thing. Okay? So that's the condition that these families have to satisfy in order to be there in the limit. And that limit is being called Zp. For the time being, it's just a set. We'll make it into a ring very soon. So because it's a subset of this direct product, there are these projection maps to the various terms of the inverse system. So from the product of a certain number of things, you have, of course, maps to each of the things, each of the factors, right? And this inverse limit being a subset of the product, you have the restriction of those projections to Zp. And those projections, I'm calling them pi m. So what does pi m do to an element of the inverse limit? It just picks the component in the ring AM, right? It takes an element of the inverse limit like this and it gives you the component xm. And obviously this map is surjective. So in particular, why is it surjective? Because each phi n is surjective. I mean, that's easy to see. And therefore, this Zp is not empty. I mean, just because you have defined something doesn't mean that there's some element in it. But it's easy to see that it's not empty, right? Now, yesterday somebody had made this remark that when I have an inverse system, and if I forget the first few terms and just keep the remaining terms, I get the same limit. It's an illustration of this fact that if I have a p-adic integer x, so it has these components xn is in the ring an. Now, if I just take a part of this p-adic integer, so xn, but n greater than this big N, that part of this p-adic integer determines the whole p-adic integer, because, for example, x capital N is not part of this portion, but x capital N is phi capital N of x capital N plus 1, and so on. On x1, for example, if you want to recover x1 from this thing, you have to apply phi n first, and then phi n minus 1, and all the way down to phi 1. You apply these things to xn, and you get x1.
Yes.
Okay, so these are all very basic remarks.
Sir?
Yes?
So instead of like taking a tail here, I mean, we could have just taken an infinite subsequence, right? Then also we could have recovered, I guess.
That's right. That's also possible. That's right. Yeah, you can do that too. Yes.
Okay, thanks.
Essentially, yeah, it should be something called cofinite or cofinal. not cofinite. Cofinal is the word, right? So if you take an infinite subsequence, which tends to, yeah, of course, you'll have to tend to infinity, etc. So then you can recover everything in between because these are images of the bigger ones. Here is some notation which I'm going to use. So if I'm given two integers a and b, then I'll denote by a, this a, b with this kind of funny brackets to be the set of all integers x in z from between a and b, possibly equal to a, but not equal to b. Okay, so this interval, normally this notation is used for the real interval, but I find it convenient to use it also for this interval in Z. So it's a finite set. It's a subset of Z consisting of those elements which are between A and B and possibly also equal to A. Similarly, for any two subsets, any two sets A and B, I'll use the notation, and this is standard, A to the power B is going to be the set of all mappings. Can you hear me? Is there some noise coming from somewhere or? Right, it has disappeared. Good. So A to the power B is going to be the set of all mappings from B to A. That's the standard notation for this thing. But sometimes we will view this A to the B as the set of all families A sub B with B in B. So families of elements of A indexed by B. Okay. So now if you look at our prime P is fixed. So if you look at the integers from 0 to P minus 1, okay, and look at families of integers from 0 to P minus 1 indexed by the integers from 0 to N minus 1. So that's one set, the families of integers between 0 and P minus 1 indexed by integers between 0 and N minus 1. This set of all these families is in natural bijection with a set of all integers from 0 to P to the power N minus 1. How is that? That's just the p-adic expansion. So you take such a family and you write down this sum. It's a sum over all I of B sub I, P to the I. And this, for example, in base 10, the digits are, there are 10 digits, 0 to 9. And if you write two digits in succession, you get all integers between 0 and 10 squared minus 1, right? From 0 to 99. So this is what is happening for an arbitrary P. Families of these, here the digits are 0 to P minus 1. Just as in the case of 10, the digits are from 0 to 9. So the base P expansion in N gives you bijections like this for every N. And of course, this set of the set 0 to P minus 0 to P to the N, there's a natural bijection to the set AN because AN is just Z modulo P to the N. So the upshot of all this is that this set 0P raised to the power 0N is in bijection with the set AN. With the, yeah, I mean, it's a ring, but this one is just a set, and I'm giving a bijection of this set with this set AN. Okay, and moreover, I mean, if you look at this square here, you have the vertical arrows are both bijections. This is the map phi n, which I've explained just now. Is the map of reduction modulo P to the N. This is reduction modulo P to the N plus 1, and this is reduction modulo P to the N. And this map is just the restriction of a family. So this is a family consisting of from 0 to, the indexing set is from 0 to n. And here the indexing set is from 0 to n minus 1. So you just forget the last digit, so to speak, right? So that you get a restriction map here. And with this definition of rho n, this diagram commutes. So I'm not saying anything profound. I'm just saying, for example, that if you take a 3-digit number and reduce it modulo, say, 10 to the power 3, you get some number. Then you just keep the last 2 digits and reduce it modulo 10 to the 10 squared, which is reduce it modulo 100. Then you get, or if you take that number modulo 1000 and then reduce it modulo 100, you get the same thing. That square commutes. Okay, so now, just as in the example which I showed you right at the beginning, the inverse limit of these, this is an inverse system here at the top. I've just written one arrow, but these arrows go, keep on going. They go all the way on the left, right? And therefore, I can talk of the limit of this inverse system. And as we saw in the first example, where we just had 2 digits, 0 and 1, that was the case p equal to 2, so to speak. And in that case, the limit consists of all infinite families of these p digits. Those 2 digits in that case, and here it's going to be all infinite families of these p digits. So that's the inverse limit of this top system. And obviously, that inverse limit has to be in bijection with Zp, because Zp is the inverse limit of these sets at the bottom. If you have one inverse system here at the bottom, another inverse system there at the top, and if you have bijections all the way, which make the triangles squares, which make the squares commute, then of course you're going to get a bijection of the inverse limit of the top system with the inverse limit of the bottom system, the system at the bottom. So what have we got now? We have got a natural bijection of Zp with this 0p to the power n. N is the set of all natural numbers, 0, 1, 2, and so on. So elements of this set, this 0p to the power n, consist of infinite families indexed by natural numbers. And the terms of those families are the digits from 0 to p minus 1 inclusive. Okay, so this is what, this is another way of seeing that the set Zp is not empty. And not only is it not empty, it has the power of the continuum. That's what the cardinality of this set 0p to the power n is. Okay, so this is called the p-adic expansion of your p-adic integer x. If I have an integer x in Zp and I look at the corresponding element of an element of the inverse system here, let's call it x, an element of the inverse system here, which corresponds to that x, is going to be called the base p, the p-adic expansion of that x. So it consists of an infinite family of digits, and the digits are between 0 and p minus 1 inclusive. Okay. So now I'm going to make this Zp into a ring. So how do one has to define addition and multiplication and say which element is the 0 element, which element is the unit or 1 in that ring. So the 0 element is the one for which xn is 0 for all n. P-adic integer x is such a family, xn, where xn is from Z modulo P to the N, and I'm going to say this element is, if each xn is 0, then I say that x is equal to 0. And if each xn is equal to 1, then I say that x is equal to 1. Okay. And I put minus x to be minus to the family consisting of minus xn, etc. The addition and multiplication are defined component-wise. So x plus y consists of the family xn plus yn, and xy consists of the family xn times yn, right? So these definitions make Zp into a ring, and in fact a subring. This is how you define addition and multiplication on the product ring, and Zp is a subring of this product for these operations, right? Okay. So let's just see what p times x is for a p-adic integer n in terms of the p-adic expansion of that integer. So if x is in Zp, and if bi is the p-adic expansion of this x, so morally x is equal to b naught plus b1 times p plus b2 times p squared plus b3 times p to the cube, p to the 3, and so on. That is what x is. And p times x, what is it going to be? I mean, if you use these definitions, you will see that it's the p-adic expansion of p times x is going to be, it's going to start with 0, and then b naught in the place of units, b2, yeah, so b naught, b1 in the place of p squared, and so on. Okay, so it's going to be b naught times b plus b1 times p squared plus b2 times p cubed, and so on. Okay, so now you see these, we considered Zp just as a set, the inverse limit of a system of sets. Now we said, no, let's consider it as an inverse limit of a system of rings. And now we are taking one more step, which is strictly speaking not very important for what follows, but it's, in many respects, it's very important, undoubtedly, which is to say that each of the rings which constitute this inverse system is actually a topological ring. So what is a topological ring? Now, it's a ring along with a topology, and I assume that people are familiar with basic topology, right? I mean, how it's defined in terms of open sets and so on, and what continuous maps between topological spaces are. So a topological ring is a ring together with a topology for which these ring operations, which are addition and multiplication, they are continuous maps. Okay, so in our case, these rings an, z modulo p to the n, these are topological rings when we give z mod p to the n the discrete topology. Of course, any ring, you take any ring, give it the discrete topology, you get a topological ring. Maybe they are not the most interesting ones, but they qualify according to the definition, and they give interesting examples in this limiting cases. So although you might say that the topology on z modulo p to the n is not very interesting, it's discrete, the topology on Zp is far from being discrete. Okay, so it's a real topology. So how do you give it a topology to Zp? One way to see it is to say that we have the product topology on the product of all these rings. And Zp is a certain subring. It's a closed subset It's a closed subset and a subring. So it gets a topology from the product, and that makes it into a topological ring. Okay, so one way of defining a topology on, let's say, a commutative group or a ring, or let's come to an arbitrary set. One way of defining a topology on an arbitrary set, as I said, it's using open sets and so on. Another way is that for each point in that set, you define a system what are going to count as the neighborhoods of that point. Of course, they have to be subject to some axioms, just as open sets are also subject to some axioms. So you can define a topology either in terms of open sets or in terms of neighborhoods of each point of that set. But if your set happens to be a commutative group and you want to define a topology which will make it into a topological group, then you just need to define all neighborhoods of the origin, because the other neighborhoods you get by translation from any 2 points. I mean, if you have some other point, you want to get the neighborhoods at that other point, you just translate you add that element to each of the neighborhoods and you get neighborhoods of that element. So so here we have the subsets Vm, which are the inverse images of 0 under this map pi m. And this, so this is what is happening. You are translating Vm by x to get a system of neighborhoods of x. It's a fundamental system of neighborhoods, of open neighborhoods. And what does that mean, fundamental system? It means that if I'm given any open neighborhood of this point x, there's one in this system which is smaller, which is contained in that neighborhood. Okay, so I'm not going to insist upon this because we are going to use the topology very little, but it's a very important feature of the p-adic numbers, of the p-adic integers, that they carry a natural topology. And moreover, this Zp is a compact topological ring because it's a closed subset of this compact ring. The product ring here is compact because each of the ANs is finite and discrete, so it's compact, and the product of a family of compact sets is compact. Okay, so here is what my final definition of Zp is. The first definition was that it is the inverse limit of a system of sets. Then I said, actually, it's the inverse limit of a system of rings. And now I'm saying it's the inverse limit of a system, of an inverse system of topological rings. Okay. So let's recall what the universal property of the limit is. It says that if I'm given a ring A and mappings Fn, mappings here mean homomorphisms of rings. Fn's from A to An such that the triangles that you can write down commute. So what's the triangle? You have maps from A to An plus 1. Yeah, An plus 1 it's called. From An plus 1 you have a map to An. You also have a map from A to An plus 1. That is going to be the map. It's going to be called Fn, and this one is called Fn plus 1, and this is phi n. So the triangle commutes means that this Fn is equal to this Fn plus 1 followed by phi n. right? Okay. So whenever you have such a system of morphisms from some ring A to all these rings AN, compatible in this sense that these triangles commute, then there's a unique homomorphism from the ring A to the ring Zp, such that these Fn's can be obtained from the Pn's, pi n's which we have using this iota, this unique homomorphism, right? And we have to prove the existence of this iota, and you just take iota A to be Fn of A, that family. That's a compatible family. Why is it compatible? Precisely because these triangles commute. It's a compatible family, and therefore it belongs to Zp, and you can define iota of A to be this family, and then you've got your iota which has this property. Okay. So here's a word about the topology of Zp, which is that if I have some arbitrary topological space X, when is a map from that space X to Zp continuous? So the answer is it's continuous if and only if, when I compose that map F with the various pi n's to get a map from X to An, those maps are all continuous. They are maps into discrete spaces, and I want them to be continuous. Okay. So this is the ring Zp of p-adic integers. It's a compact. Maybe I have not yet this. Yeah, it's a compact ring for the time being. Now, another ring which is very similar to Zp in many of its properties, but which has characteristic P. By the way, this ring Zp, of course, I said yesterday that it should not be confused with Z modulo Pz, which is what some people denote with the notation Zp. But it should not be confused with Fp par series T either. So what is that ring? This Zp doesn't have characteristic P, okay? So this Fp par series T, instead of Z, you take this ring, Fp polynomial ring in one indeterminate T. Take this ring B and define Bn to be B modulo T to the n B. T to the n generates an ideal in the ring B. I go modulo that ideal to get the quotient ring Bn. And of course, the ideal generated by T to the n plus 1 is contained in the ideal generated by T to the n. So I get a map from Bn plus 1 to Bn. All this phi n, I mean, it's a surjective map. It's reduction modulo T to the n, so to speak. And that defines an inverse system. These phi n define an inverse system. And I can take the inverse limit, right? This inverse limit is denoted Fp par series T. So it consists of a typical element of Fp par series T will look like A0 plus A1T plus A2T squared, where the coefficients Ai come from the field Fp, and the powers of T, there are infinitely many powers of T involved. Infinitely many of these coefficients may be non-zero. So if only finitely many of them are non-zero, then you get a polynomial, but you allow infinitely many of them, I mean, you allow all the coefficients to be arbitrary, then you get this par series ring, right? So we will come back to this after a couple of lectures. So for the time being, we are looking at Zp. And of course, there's a natural map from Z to Zp, natural homomorphism of rings. That's there. There's a homomorphism of Z to any ring whatsoever, right? But in this case, I claim that this homomorphism is injective. So that's one way of seeing that Zp doesn't have characteristic P, right? Because Z is, the map from Z to Zp is injective. Now, how do I show that this map is injective? So let's take something whose image is 0. If the image of something is 0, it means that when I go down to M, I get 0 for every M, right? In other words, the element of Z, which goes to the 0 element in Zp, has to be divisible by p to the m for every m. It has to be divisible by p, p squared, p cubed, and so on. And of course, there is only one element in Z which has this property of being divisible by p, p squared, p cubed, and so on. That's the element 0. So this map is injective. Okay. So, and therefore we can identify Z with the subring, which is the image of this unique morphism into Zp. Okay. So here comes the first fact about this ring Zp. It says that the multiplication by p to the m map, if you have a ring A and element x in that ring, you can take the map from A to A, which sends everything to x times that thing. That's the multiplication by x map on the ring A. Here I have the ring Zp, I have the element p to the m in Zp, and I'm looking at the multiplication by p to the m map on this ring Zp. So it's being claimed that this map is injective, first of all. And the image of this map is, of course, p to the m times Zp. It's being claimed that this image is the kernel of Vm. What is Vm? That's a name for the kernel of Zp to m, Am, that homomorphism of rings. You take a family of a p-adic integer and just look at the mth component, so to speak, right? That's pi m. So let's look at the statement. P to the m is injective, and this ideal is the kernel of this pi m. So to show the injectivity, we just need to show it for m equal to 1, because p to the m is obtained by multiplying by p repeatedly, right? And if each of the maps is injective, then of course their composite is also injective. So we are trying to prove that x going to p times x is an injective map on Zp. Now, one way to check this is to look at the p-adic expansions, right? You look at the p-adic expansion of x, and I've already told you what the p-adic expansion of p times x looks like. It's just the same expansion, except that it's shifted one step to the right, and a 0 is inserted at the beginning. So of course, if I mean, that clearly shows that this multiplication by P map is injective. So, but there's another proof. So I'll allow you to look at it for 2 minutes while I take a sip of water. So take a look at this. Okay. So there we are. So what does it say? If Px is 0, I want to get a contradiction by this, or I want to conclude that x has to be 0 if Px is 0, and x is this element in Zp, then of course P to the n plus 1, P of P times x to the n plus 1 is 0 for every n, which means that there is some y n plus 1 in a n plus 1, such that this x n plus 1 is P to the n times this y n plus 1. That's how this group a n plus 1 is. You know, if some element has order p, then it's p to the n times some other element, because anyway. So then you look at xn, it's going to be phi n of this xn plus 1 by definition, right? And then I can take this p to the n out and you get 0. So xn is 0 for every n, and this element x itself is 0. Okay, so now I have to show that the kernel of pi m is this, the image of multiplication by p to the m. So one of the inclusions is clear. The image of p to the m, multiplication by p to the m, is contained in Vm, right? That's that's obvious. Let's prove it in the other direction. So again, one way to do it is to use p-adic expansions, but you can also do it more directly. So I take x in Vm. I have to show that x is in the image of p to the m, right? So x in Vm means xm is 0. So xm plus r is in p to the m for every r. P to the m times a m plus r for every r, right? If xm is 0, then xm, this is basically saying that xm plus 1 is killed by p to the m, xm plus 2 is killed by p to the m, etc. Or rather, not killed. It's in the image of multiplication by p to the m. Okay, but we had this short exact sequence right at the beginning. We established that you have this short exact sequence. 0 goes to AR, goes to AM plus R, goes to AM, goes to 0. Okay, and that means that, you know, there is a unique map from AR to AM plus R, such that this iota R of 1 is P to the M. Okay. So the image of this map is this ideal, and therefore there's a unique YR in AR such that x to the M plus R is iota R of this YR. Now you verify that this phi R applied to YR plus 1 is this YR. In other words, these YRs form a compatible family, and this X, which we wanted to show belongs to P to the M times Zp, we have found a Y such that X is equal to P to the M times Y. Okay. So this is summarized in this exact sequence. P to the M Zp, that's the ideal generated by P to the M in Zp, and the quotient has been identified with Z modulo P to the M Z. Okay. So, in other words, if I go modulo P to the M in Z or in Zp, I get the same thing. I get the same quotient. Okay. Okay. So this is somewhat a general kind of a statement, which I don't need for the time being, so I'm going to skip this. Let's come back to our ZP and let's determine when an element of ZP is a unit. When is it invertible in ZP? So there are these three conditions which are being claimed to be equivalent. An element X is in ZP star. This notation stands for the group of invertible elements of the ring ZP. In general, if I have a ring A, then A star stands for the group of invertible elements of that ring. So X is in ZP star. That's one condition. The second condition is that X is not in the ideal generated by P. X is not in P ZP. There's a second condition. And the third condition is that pi 1 of X, so the first component of X, so to speak, which comes from Z mod PZ, that should be non-zero. You know, for the first thing, ZA1 or Z mod PZ is actually FP. And to say that something is invertible in FP is the same as saying that it's non-zero. It's different from zero. So these three conditions are equivalent. So in particular, this PZP, this ideal, is the unique maximal ideal of the ring ZP. Because anything outside this ideal, anything outside is invertible. Okay? So, so 2 and 3 are equivalent, of course, because this FP is really can be thought of as Z modulo PZ. That's what we saw here. For Z modulo P to the M, it can also be thought of as ZP modulo P to the M. Okay? So 2 and 3 are equivalent. And 1 implies 2 is clear, right? Because this, if an invertible element belongs to an ideal, then it has to be the whole ring. Whereas we know that it's not the whole ring. The quotient is Z mod PZ. So 1 implies 3 is clear. So all we need to prove is that 2 implies 1. So if X is not in PZP, then it's invertible in ZP. So let's suppose that X is not in PZP, then its first component, pi 1 of X, is going to be invertible in FP, right? And so in every xn has to be, no xn can be in PAN, right? Because otherwise x1, which is the image of xn, will become invertible in Z mod in A1, right? So there exist yn and z1, yn and zn in an such that xn yn is equal to 1 minus p zn. Or equivalently x, I mean, this is, so if I put xn prime equal to this, I get xn prime equal to 1. Okay, so basically I've got these elements xn prime for every n, and it must be easy to check that phi n of xn plus 1 prime is xn prime. So you get a compatible family of these elements, and they define a p-adic integer x prime, which shows that xn, which has the property that when you multiply it with x, you get 1. So x is invertible in ZP star. Okay, so now, in fact, this group of invertible elements itself can be realized as the inverse limit of these groups of invertible elements. You know, you had this inverse system of rings. but you can also form an inverse system of the multiplicative groups of these rings. And the inverse limit of that inverse system of multiplicative groups is the multiplicative group of Zp. Okay. So another thing which, another ring which you have is Z bracket P. I don't know how many people are familiar with this, but this is what is called localization. So if you have some ring A and a multiplicative subset S of A, then you can define S inverse of A, which is the ring obtained by inverting everything in S. Here, S is the multiplicative subset of Z, consisting of all integers which are not congruent to 0 mod P. So it's the complement of the ideal PZ. Everything which is not in the ideal is in this multiplicative set S. A multiplicative set is something which contains the product of any two elements it contains. So why is the complement of PZ a multiplicative set? Because if I take two elements which are not in PZ, the elements of Z which are not in PZ, and I want to show that their product is not in PZ either. How do I show it? The modulo P, these two elements which I have, they go to non-zero elements because these two elements are not in PZ. Their product is also non-zero because modulo P, what I've got is an integral ring, in fact, a field. So the product of two non-zero elements is non-zero. So their product here in Z cannot belong to PZ. Okay, so S is a multiplicative set, the complement of PZ. When I invert everything in S, another way of thinking of this Z bracket P is as the subring of Q obtained from Z by adjoining 1 over L for every prime L different from P. You have fixed a prime P. Now there are many other primes, of course, and they have inverses in Q. You take the smallest ring containing all those L inverses, where L is a prime different from P. Of course, that smallest ring will contain the ring Z. So Z, along with these L inverses, where L is a prime different from P, that's the ring Z bracket P. Z parenthesis P. Okay. So a third way of thinking of this ring S inverse Z is by its universal property, which is that whenever I have a map from Z into some other ring, let's call it B, which takes everything outside PZ to an invertible element, there's a unique map from this S inverse Z, which is also being called Z parenthesis P, to that ring B, which makes this triangle commute. Okay, so okay, so what is being said here? It's being said that okay, now so it's being said that there's a unique morphism of rings iota from Z parenthesis T to ZP. Why is there a morphism of rings at all? Because of course there's a morphism from Z to ZP, and elements which are not in the ideal PZ are being taken to invertible elements in the ring ZP. And that's the universal property of this Z parenthesis T, that whenever I have a map from Z to a ring, which takes elements outside the ideal PZ to invertible elements, I have a unique map from Z parenthesis P to ZP, which makes this triangle commute. So I get this unique map from ZP to Z parenthesis P to ZP. Okay. And why is it injective? So to see that it's injective, I take an element X in Z parenthesis P, which goes to 0. And going to 0 means that X is congruent to 0 modulo P to the N for every N. But there's only one element in Z parenthesis P, which is divisible by P to the M for every M. That's the element 0. So this map is injective, and therefore there's an induced map. I mean, from Z parenthesis P modulo P to the M to ZP modulo P to the N. And this is an isomorphism of, you can see it in various ways, because both of them are isomorphic to ZP and so on. So this is an isomorphism. Okay, so the next assertion I want to make is that every non-zero X in ZP can be uniquely written as X equals P to the M times U, where some M in N is the set of natural numbers, so 0, 1, 2, and so on, and U is a unit or an invertible element of ZP. So every X can be uniquely written in this way. Okay. So here's the proof. It's not very long. It says that there has to be a smallest M such that, so X is not 0, means that, you know, when you think of this X as X1, X2, X3, all these, the Xi belonging to the ring AI, then one of the Xi's is non-zero. And there has to be a first one which is non-zero, because X itself is non-zero, right? So take the smallest M such that pi M plus 1 of X is non-zero. And then we have X equal to P to the M U. I mean, this is what we have proved earlier. So by the way, at various points in the notes, there are these question marks. So these question marks refer to something which we are already proved. And you are supposed to figure out what is being used here and which result is needed, which result have we proved earlier, which is being used here. So, for example, here it says, by this thing, U is in ZP star. So what is this question? What do these question marks stand for? I believe that they stand for this assertion, this E. So something is not in PZP is equivalent to X being in ZP star. That is what is being used here, right? We had something not in PZP, and then we are saying that it is in ZP star. So that was the statement being used here. So moreover, this statement, so this first you get a decomposition like this, and then this uniqueness is also, it follows from the injectivity of this map, multiplication by P to the M. It's injective, so basically you can cancel out P to the M, and you get uniqueness. Okay. So now let's take an element X in ZP, non-zero element. So you can write it as P to the M times U, where U is invertible. And this M is uniquely determined by X. So let's put VP of X equal to M. Now, this VP is called the p-adic valuation of X. And since we are taking X non-zero here, we also define the p-adic valuation VP of 0 to be plus infinity. Okay, so VP is a map from the non-zero elements of Zp to Z, and oh, wait a moment, to N. It will become Z when we come to QP. So for the time being, this M is a natural number, and except for 0, where we allow this plus infinity. So we have these three equivalent conditions here in this statement. These three equivalent conditions, they are equivalent to this fourth condition in terms of VP, that VP of X should be 0. For X to be invertible, it's necessary and sufficient that this M should be 0. So another thing which is clear is that VP of X times Y is VP of X plus VP of Y. Okay? And here is a very important fact, which says that if I take VP of X plus Y, then it's at least, it's greater than or equal to whichever is smaller, VP of X, VP of Y. Whichever among these two is smaller, VP of X plus Y is larger than the infimum of these two. And in fact, if you have, if these two have different valuations, if VP of X is different from VP of Y, then we actually have equality here instead of this inequality, a large inequality, right? Sometimes people use the term large inequality when equality is one of the possibilities, when equality is allowed. And so if these two are different, then you actually have equality instead of this large inequality. Okay, so now let's come to the ideals of this ring. Yeah, there's a question.
So the lectures are till 4:30 or 4?
4:30.
Okay.
Yeah. Okay, so now this statement says that the ring Zp is integral in the sense that the product of any two non-zero elements is non-zero, and moreover, every ideal in this ring, non-zero ideal, is generated by a power of p, by an appropriate power of p, right? So basically the ideal theory of this ring is very simple. You have this element p, it generates an ideal p Zp, and all the other ideals are powers of this ideal. All the other non-zero ideals are powers of this ideal. So how do we prove this? So first we want to prove that it's integral. So I have to take two non-zero elements and show that their product is non-zero. So take X and Y, which are non-zero. What is the VP of X plus Y going to be? Is the VP of X plus the VP of Y. Here's the computation. And if X and Y are non-zero, then these two are different from plus infinity. So their sum is different from plus infinity. And therefore, XY is non-zero. Okay? It's more interesting to determine the ideals. So let's take a non-zero ideal A. Now, it's non-zero, so it has elements which are non-zero. And non-zero elements have VP, which is a number which is not plus infinity. So let's take an element which is the smallest VP, which has the smallest valuation, a non-zero element in the ideal A, which has the smallest valuation. Let n be that valuation. And the claim is that this ideal then is the ideal p to the n Zp. Okay, so x is this element which has the smallest valuation. Vp of x is equal to n. Then, of course, x is p to the n times alpha, because that's how Vp is defined, right? Vp is the exponent of p in this decomposition of x, where alpha is some unit. So you can write, I mean, you can rewrite this as p to the n equals x times alpha inverse. So p to the n belongs to this ideal, right? So the ideal generated by p to the n is contained in the ideal A. Now you have to prove equality, that A is actually equal to this ideal. So if I take a non-zero y in the ideal A, Vp of y is going to be greater than n by the definition of n is the smallest value, it's the smallest valuation of a non-zero element in A. So y is going to be Vp of y minus n times b times p to the n. I mean, it's I've written p to the n here, and to compensate for the minus n here, for some b, right? So some beta. So, and therefore this y, as you can see, its y is in the ideal generated by p to the n. Okay, this is, I mean, this is in Zp because precisely because Vp of y is greater than n, and therefore this is a positive power of p. And so A is contained in the ideal generated by Zp, by p to the n, right? So since you have inclusions in both directions, this A has to be equal to p to the n Zp. Okay, so now there's this, some of you might have come across metric spaces. So there's a distance on a set, right? So you can define a distance on Zp, and you can actually define what is called an absolute value on Zp. So the absolute value of an x, of a p-adic integer x, is defined to be p to the power minus Vp of x, for if x is non-zero, and the absolute value of 0 is 0. This is the p-adic absolute value. You have p in the subscript here. Okay, so you define the absolute value of a p-adic integer. Notice that if the absolute value of 0 is 0, that's natural. But the absolute value of p itself, what is it? If I put x equal to p here, then I get p to the power minus Vp of p. Vp of p is, of course, 1. So it's p to the power minus 1. So the absolute value of p is 1 over p. The absolute value of p squared is 1 over p squared. That's smaller than the absolute value of p. The absolute value of p to the n is 1 over p to the n. So, in fact, the higher the power of p, the smaller, the closer the absolute value is to 0. Okay. So, and if so the absolute value of the difference of x and y is smaller than the larger of these two. Okay, this follows, this cannot be very difficult to derive from this inequality here about the valuations. Okay, the valuation of a sum. I mean, of course, here instead of a sum, I could also write difference. Okay. So the absolute value of the difference of x and y is at most equal to the supremum, the bigger of the two absolute values. And if these two absolute values are different, then you actually have equality here. So not only do you have this absolute value on Zp, you have this p-adic distance on Zp. So the distance between 2 points x and y in Zp is going to be the absolute value of x minus y. And this condition here on the absolute value translates into this inequality. So distance in a metric space, the distance satisfies some natural axioms, right? One of the axioms is the triangle inequality. And that would say that the distance from x to z is smaller than the sum of the distances from x to y plus the distance from y to z. Here, you not only have that inequality, you have a much stronger inequality. It says the distance from x to z is less than whichever of these two distances is larger. Okay, so of course, then therefore it's smaller than the sum of these two distances, but it's actually smaller than whichever of these two is bigger. Okay, so when you have a distance, you have a topology defined by that distance, but we already have a topology on Zp, right? The inverse limit topology, and for which I gave you a fundamental system of open neighborhoods of the origin, and therefore by translation of any point, any p-adic integer. So what is being claimed here is that the topology on Zp is the same as the one defined by this distance dp. And here is a small checking which does this. I'll not go into it because I'm not going to use these things very much. Okay, so I have a couple of minutes more. Yeah, so some remarks. There's this notion of a totally disconnected topological space. Okay, so what is that? In general, you have the notion of connected components of a topological space. And the connected components are a partition of the space. But if each point is reduced to a connected component, then you say that the space is totally disconnected. That's a kind of topology which is very different from the reals or the complex numbers with which we are familiar. So the topology on Zp is totally disconnected in the sense that given any 2 points, there are no 2 points which are contained in a connected subset. Okay. Okay. Here's the reason. So why is it true that for any 2 points in Zp, no two are contained in a connected subset? Of course, the points have to be distinct. The reason is that I can find a continuous map from Zp to some discrete space, which takes the first point to 0 and the second point to 1, let's say, or which takes these 2 points to 2 different points in the image. And that is true in Zp because if x is different from y, then there's some index, some power of p modulo which they are different. And the map from Zp to Zp modulo p to the n is of course continuous, and the images of x and y are different. Z modulo p to the n is a discrete space in which x and y have distinct images, and therefore they cannot be in a connected set, right? Because the continuous image of a connected space is connected. Okay, so another remark is that we define Zp as the inverse limit of a certain inverse system. Another way to define it would have been to define this p-adic valuation of elements of Z, of integers. So that defines a distance, and you could complete Z for that distance, and you would get Zp. Okay, so now we want to show that, that p-adic expansion of a p-adic integer, we were just thinking of it as a family of digits, but in a certain sense, that integer is actually a limit. So that family has partial sums, right? You can add on any finite number of terms in that family. So x is actually the limit of these partial sums. So that's the claim, and here is the proof. So you have these partial sums Sn, which are the sums of the first n terms in that p-adic expansion. And so we fix an integer m. So we said that these things form a fundamental system of neighborhoods, of open neighborhoods of the point x. So in order to show that these Sns tend to x, I have to show that no matter which m is given to me, almost all Sns are in this neighborhood of x. So here is the proof. You just take n to be greater than n, then Sn minus x is in this, and therefore you have what is required, that Sn is in this open neighborhood. Okay, so for example, what's the p-adic expansion of -1? It's the digits are p minus 1, p minus 1, p minus 1 all the way. So, and what is the p-adic expansion of 1 minus p? 1 minus p is invertible, of course. Why? Because it modulo p, it's non-zero, so it has to be invertible. So its inverse has to be a p-adic integer. Which integer is it? Or in other words, what's the p-adic expansion of 1 minus p inverse? It's this one. Okay. And so the final thing is that the subset n is a subset of Z, which we have realized as a subset of Zp. So the claim is that Z is dense in Zp. In fact, I could take any b which is prime to p and any a in Z, then this sort of translated bn, a plus bn, is dense in Zp. So to show that something is dense, it's enough to show that for every n, its image in Zp modulo p to the n is the whole of Zp modulo p to the n. And that is what is being shown here. Okay. Right. So let us summarize what we have done today. We have seen that we have this ring Zp. It carries a certain natural topology, but that topology is not going to be very, very crucial for what we do. It is defined, anyway, so it is defined as this projective limit. It is an integral ring in the sense the product of any two non-zero elements is non-zero. It is local, but not a field. It's not a field because P is not invertible in Zp. It's local in the sense of having a unique maximal ideal. And that maximal ideal is p(Zp). Why is it the unique maximal ideal? One way of seeing it is that, oh, we have determined all the ideals of this ring. And by inspection, p(Zp) is the only maximal ideal. You know, the other ideals are p to the n Zp, modulo which the quotient is just Z mod p to the n, and that's not a field. Okay. This maximal ideal is principal. Of course, it's generated by P, for example, and it's p-adically complete in the sense that, so here's the sense in which it is p-adically complete, that if I take the ideal generated by P, in fact, and if I take the inverse system given by the powers of that ideal, in other words, if I take the inverse system given by the powers of P, by the ideals in the powers of P, you take the corresponding quotients and they form an inverse system. The inverse limit of that inverse system is Zp. For example, Z is not two-adically complete because, or three-adically complete, it's not. Because when I take Z and take the ideal generated by 2, take the powers of this ideal, look at the inverse system given by these powers, namely Z modulo 2, Z modulo 4, going to Z modulo 2, Z modulo 8, going to Z modulo 4, and so on, and I take the inverse limit of this, I get something which is not Z at all. So Z is not two-adically complete. Zp is p-adically complete because when I take the powers of P and look at the ideals generated by these powers of P and look at the inverse system given by Zp modulo P, Zp modulo P squared, Zp modulo P cubed, and so on, and look at the inverse limit, I get back Zp. So Zp is p-adically complete in this sense. So later we will look at other rings which are p-adically complete, and that's it. I mean, I've run out of time, so I'll stop this for today. And if you have any questions, actually, you can send me emails as well, right? Okay. So we'll see you next week on Monday, and you have a tutorial on Friday at 3. That's only a 1-hour tutorial. Okay. Good afternoon.
Sir?
Yes.
Sir, I want to ask that where do we find lecture notes and videos of videos?
Okay, so the videos will get uploaded, but the lecture notes, I've shared a link with you all. You don't have the link?
Actually, sir, the last link you have shared, I was not able to access that. It was saying that the file does not exist.
Okay, and this is very strange. I'll let me share the link in the chat box just now. So here it is. So here is the link in the chat box. Can you just see if it works? Hello? Does the link work?
Yes, sir. Yes, sir. It's working.
Okay, okay. So see you on Monday.
Sir, but lecture 0, sir, link was not working.
Lecture 0, what about it?
So that link was not opening.
But now things are working?
Sir. Yes, sir. Okay.
Okay,
No,
good.
no, in that shared PDF, you can get the 0 lecture.
Okay,
0
okay.
lecture is there. Lecture 0 is there.
Yeah,
Okay, sir. Thank you, sir.
right. Okay then.
Sir,
Yes.
I had a question. So, like the exercises that you have given in the notes, I mean,
Yeah.
shall we like solve and submit them or something like that?
No, no, you don't. No, this is not a regular course of your whatever college or something. This is for people who are interested in learning this stuff. So you are encouraged to solve them, but of course, there's no requirement to submit them to me or to anybody. For your testing your own understanding, it would be a good idea, of course, to try to solve most of the exercises, but you don't need to submit them to me.
Okay, sir.
Okay. See you on Monday.